Lesson 1. Introduction to Flow Models. This lesson is about flow models used in computational fluid dynamics software to predict fluid flows. The main objectives of this lesson are to recall the basic equations, which are usually taught in courses on theoretical fluid dynamics, and to distinguish the difference between viscid, viscous laminar, and turbulent flow, because this is important for the correct application of CFD to solving practical flow problems. Viscid fluid does not stick to a wall. The wall is simply a constrained surface that cannot be crossed by fluid, that is, velocity is tangential to the wall. Viscid flow describes only qualitatively the relationship between pressure and velocity. When the velocity increases, the pressure reduces, and the pressure has a local minimum in a vortex, etc. Viscid flows are therefore not realistic and cannot be realized in an experiment. There is no pressure drop in a straight duct or pipe, and no forces on submerged bodies when the fluid is inviscid. A special class of inviscid flows with an irrotational velocity field are called potential flows. They are described by a single Laplace equation for the velocity potential phi. The velocity field is then defined by the gradient of potential V equal minus grad phi. Potential flow models are still used with some tricks in the design of turbomachinery, especially for ship propellers. Also, methods based on potential flow are used to simulate seakeeping and maneuvering of ships. Euler equations describe more general inviscid flows which may be rotational. They are still sometimes used to simulate flows in external aerodynamics. Euler equations consist of the mass conservation equation, given here, and momentum conservation equations given by this equation. These equations contain the rate of change term, the convection term, and on the right hand side, the momentum equations contain the pressure gradient term and the body force term. Here ρ is the density, v is the velocity vector, p is pressure, and b describes the vector of body forces. The momentum equation is a vector equation. It produces three equations for the velocity components. Simcenter STAR-CCM Plus offers the possibility to compute inviscid flows either by choosing the inviscid fluid model or by setting the fluid viscosity to 0. Because the inviscid fluid does not stick to walls, there are no boundary layers or recirculation in inviscid flows. This means that the computational grid can be significantly coarser than when computing viscous flows, which leads to a lower computing effort. Laminar flows are described by the Навье-Stoksa equations, which represent an accurate model for a realistic motion of a viscous fluid. The Навье-Stoksa equations consist of the mass conservation equation, also called the continuity equation, and the momentum conservation equation. These equations contain the rate of change term, the convection term, the diffusion term, and the source term. The stress tensor T contains contributions from pressure, from fluid compressibility, and from viscous forces, where D is the rate of strain tensor, which is defined as 1/2 of the gradient of velocity field tensor plus the transpose of it. Mu is the dynamic viscosity of the fluid, which is determined experimentally. Laminar flows can be very accurately predicted with moderate resources. Flow in straight channels and pipes are usually laminar up to the Reynolds number of around 2000. Transition to turbulence may occur at lower Reynolds numbers if the cross-sectional area varies, when walls are rough, or when other disturbances are present. Transition can be also postponed by ensuring a perfect geometry and no vibration or any other disturbances, but the flow usually cannot be maintained laminar for a long time. Laminar flows can be steady or unsteady and may exhibit all the major flow features like boundary layers, shear layers, separation, recirculation, etc. In channels and pipes, laminar flows result in pressure losses due to friction at walls and geometry changes if present, like expansion or constriction, obstacles, etc. The Навье-Stoksa equations describe accurately both laminar and turbulent flows. However, turbulent flows include fluctuations of velocities and pressure over a huge range of scales, both in space and in time. This is why the direct numerical simulation using Навье-Stoksa equations is not practical except at relatively low Reynolds numbers. Turbulent flows at high Reynolds numbers are usually simulated by solving the Reynolds average Навье-Stoksa or RANS equations. They are based on splitting the instantaneous value of each variable into a sum of the time or ensemble averaged value plus the fluctuation around the average. When the averaging is then applied to the Навье-Стокса equations with the above substitution, all terms linear in fluctuations disappear because by definition the average of a fluctuation is equal to 0. What remains are terms involving averaged variables and the average of products of fluctuations. For an incompressible fluid, the Rance equations contain the mass conservation equation and the momentum conservation equation, which look the same as for the Навье-Стокса equations, except that there is one additional term here. The overbar denotes time averaged or ensemble averaged mean values, and prime denotes fluctuation around the mean. The additional term in the momentum equation is the divergence of the Reynolds stress tensor. It is a symmetric tensor with 6 non-zero components. In addition to Rance equations, one has to solve one or more additional transport equations for scalar variables according to the chosen turbulence model. The Rance equations do not resolve any of the turbulent fluctuations. The complete turbulence spectrum is modeled. Most widely used are eddy viscosity types of turbulence models from the K-epsilon or K-omega families, which express the Reynolds stress tensor analogously to the viscous stress tensor using the concept of turbulent viscosity. In these models, one solves equations for turbulent kinetic energy K and either turbulent dissipation rate epsilon or specific dissipation rate omega, which are used to compute the eddy of turbulent viscosity. Turbulent viscosity is a property of the flow and not of the fluid. It can vary by 4 orders of magnitude or even more within the flow domain. When turbulent viscosity is added to the fluid viscosity, the momentum equations look the same as for the laminar flow. But the high variation of turbulent viscosity and its dependence on velocity gradients makes the solution of Rance equations more difficult. Another approach between Reynolds average Навье-Стокса equations and direct numerical simulation is called large eddy simulation, in which the Навье-Стокsa equations are spatially filtered. The larger spatial and temporal scales are resolved, and the smaller scales are modeled. Here is one example of a direct numerical simulation of flow around a sphere at the Reynolds number of 5000. The upper plot shows the instantaneous distribution of vorticity compared to the visualization of the flow using dye in an experiment. The animation on the right shows large eddy simulation of flow around sphere at a 10 times larger Reynolds number equal to 50,000. You can now imagine what happens when the Reynolds number is increased by another order of magnitude. The conclusions from this lesson can be summarized as follows. Before attempting to simulate a particular flow, one needs to decide which flow model to apply, in viscid, viscous laminar, or viscous turbulent. One then needs to define and apply appropriate initial and boundary conditions. Equations are the same for all flows. The individual solutions are defined by the initial and boundary conditions. This requires some basic knowledge about the particular flow, like Reynolds number, steady or unsteady, important physics that need to be captured like boundary layers, flow separation, etc. This knowledge helps to design an optimal computational grid and to choose where local refinement should be applied to obtain maximum accuracy with available resources. In addition, one needs to choose the best suited physics models and other simulation parameters. What remains then is to perform the simulation and to analyze the solution. Thank you for your attention. Lesson 2. The test case and computational grids. This lesson is about the test case used to demonstrate the application of CFD to solving flow problems and about computational grids. The main objectives of this lesson are to recall the boundary conditions applicable to the prediction of various flow regimes in the same solution domain, like inlet, outlet, symmetry plane, and wall boundaries. To recognize the major flow features found in ducts with a varying cross-section, like flow acceleration and deceleration, flow separation and recirculation, boundary layers and shear layers, and energy loss due to friction and geometry changes. And finally, to explain how expected flow features affect the design of the computational grid. The test case used to demonstrate the application of CFD to solving flow problems represents the flow in a channel with a semicircular obstacle on one wall. The plot on top shows the complete flow domain for the computation of the turbulent flow. The height of the channel is 10 centimeters. The semicircular obstacle with a radius of 5 cm blocks half of the cross-sectional area. The channel extends to 0.5 to 0.8 meters upstream and 0.8 to 1.8 meters downstream of obstacle depending on flow regime, shortest for an inviscid and longest for a turbulent flow. The CAD model has been created using the CAD tool in Simcenter STAR-CCM Plus software. First, a sketch in the XY plane is created and then extruded in Z direction by 2 mm. Boundaries are named to allow easier creation of reports, monitors, and plots. The following conditions are applied at the boundaries of the solution domain. Velocity inlet is applied at the inlet boundary. All variables except for pressure are prescribed. Pressure outlet is applied at the outlet boundary far downstream of obstacle. A constant pressure is specified at the boundary, while velocities are extrapolated from inside. No-slip wall condition is applied at all wall boundaries. Velocity is set equal to wall velocity, which is here 0, while pressure is extrapolated to the boundary from inside. Finally, symmetry plane conditions are applied at the front and rear plane of the solution domain. The normal velocity components is set to 0 at the boundary, while the zero gradient condition is applied to all other variables in the direction normal to the boundary, thus leading to an effectively two-dimensional flow in this thin slice. This test case was chosen because it involves many important flow features phenomena as seen in the plot of streamlines from a laminar flow. It has boundary layers along no-slip walls. It has flow separation due to the presence of an adverse pressure gradient along a wall, and recirculation. It has shear layers with high velocity gradient between fast and slow moving fluid away from wall. And it has flow acceleration and deceleration due to the change of the cross-flow sectional area. The plot on the left shows a typical distribution of velocity vectors in a boundary layer when the grid resolves the boundary layer all the way to the wall. This is called the low-ray approach. It has nothing to do with the Reynolds number of the bulk flow. An optimal design of local grid refinement is important for achieving the highest accuracy with the affordable computing effort. Local grid refinements depend on expected flow features. Boundary layers at walls require grid refinement in wall normal direction. If the boundary layer should be fully resolved, about 20 prism layers are needed. If wall functions are used, 5 to 10 prism layers may be sufficient. Flow separation from a smooth surface requires a fine grid around the separation line to capture its position accurately. Recirculation zones are very important. Most often they are undesirable. Therefore, the grid needs to be refined where they are expected to accurately capture their location and size. Shear layers require a locally refined grid because they can cause instabilities, transition to turbulence, and vortex shedding. In general, the grid needs to be finer in zones of rapid variation of variables, pressure, velocity, etc., compared to zones of moderate variation. Let's check grid features for the computation of inviscid flow. The top figure shows the coarse grid for the complete solution domain. The lower plot shows a zoom into the grid around the obstacle. Grids were refined using the refinement factor of 2. This means the grid spacing is halved in both x and y direction. The solution is expected to be symmetric around the obstacle, and therefore the grid is also refined in a symmetrical manner. The grid is made finer near the obstacle wall because the highest gradients are expected there. At inlet, a constant velocity of 1 meter per second is specified. Density of fluid is set to 1 kg per cubic meter and viscosity is set to 0. Let's now check the grid features for laminar flow. The top figure shows the coarse grid for the complete solution domain. The lower plot shows a zoom into the grid around the obstacle. Grids were refined using the refinement factor of 2, that is, the grid spacing is halved in both x and y direction. Because flow separation and recirculation are expected and boundary layers develop along walls, the grid has prism layers along all walls. It is locally refined downstream of obstacle in a larger region to capture the recirculation zone. At inlet, a parabolic velocity profile is prescribed, with the analytical solution for fully developed channel flow, with mean value of velocity equal to 1.3333 meters per second. Fluid density is 1 kg per cubic meter and the viscosity is 0.001 Pascal second. This gives Reynolds number of 133.33. Finally, let's check grid features for turbulent flow computation. The top figure shows the coarse grid for the complete solution domain. The lower plot shows a zoom into the grid around the obstacle and in its wake. Grids were refined using the refinement factor of 2, which means that the grid spacing is halved in both x and y direction. 6 prism layers are created at all walls with the stretching factor of 1.2. Because the recirculation zone is longer in the case of turbulent flow than in the case of laminar flow, the size of the solution domain and the grid refinement zones are also made longer. The channel extends to 0.8 meters upstream and 1.8 meters downstream of obstacle. At inlet, a constant velocity of 10 meters per second is prescribed. Fluid is water with a density of 1000 kg per cubic meter and dynamic viscosity of 0.001 Pascal second. This leads to the Reynolds number of 1 million. To summarize, the more we know about the expected flow features, the better can we adapt the computational grid to the flow. A uniform grid is seldom optimal. The ideal grid is the one on which the discretization errors are uniformly distributed. This means that inevitably a non-uniform grid is required in almost all practical applications. The grid needs to be locally refined with smaller spacing where the variables vary more strongly, or where specific critical features need to be captured accurately, like flow separation location. Thank you for your attention. Lesson 3. Simulation of inviscid flow. This lesson is about simulation of inviscid flows in ducts with a variable cross-section geometry. The main objectives of this lesson are to apply a CFD tool, here Simcenter STAR-CCM+, to simulate the inviscid flow in the selected test case. To analyze the obtained solutions to understand the flow physics, like relation between velocity and pressure variation. To evaluate the accuracy of solutions by comparing results obtained with different grids, and to explain the influence of the order of the discretization scheme on the accuracy of the solution for the given computational grid. The physics models selected for this simulation are constant density fluid, inviscid flow, segregated flow solver, for which we need to choose the convection scheme, which is here selected as second order, and the steady state flow. The following boundary conditions were imposed at the solution domain boundaries. Symmetry for front and back planes. You can see here the names of boundaries as given in the CAD tool during creation of CAD model of solution domain. No slip wall condition for the top boundary, bottom boundary, and semi-cylindrical obstacle. And then inlet at the left boundary and outlet condition at the outlet boundary. These two plots show the distribution of pressure and the streamwise velocity component computed on the fine grid. Pressure distribution is symmetric, hence zero net force on obstacle in flow direction is obtained. The velocity field should also be symmetric. Disturbances on the downstream side are due to numerical errors. Streamwise are smooth and almost perfectly symmetric around the obstacle. They are colored by the velocity magnitude. A comparison with pressure and velocity contours shown before reveals where the lowest velocities are found, which is at the corners upstream and downstream of the obstacle, pressure has the highest values. Where the highest velocity is obtained, which is at the top of the obstacle, pressure has the lowest value. This plot shows the variation of the streamwise velocity component along top and bottom channel walls. The obstacle blocks 50% of the channel cross-section, so the mean velocity above the obstacle doubles. However, velocity is not uniform above the obstacle. At the top wall, the maximum velocity is about 1.8 times higher than at the inlet, while at the top of the obstacle, it is about 2.6 times higher. Velocity goes to zero at both upstream and downstream corners. As the grid is refined, the solution becomes perfectly symmetric. Downstream of the obstacle, velocity should ideally be equal at both walls, as is the case upstream of obstacle. Due to discretization errors, there is a small difference. In reality, velocity would be zero at walls, but in an inviscid fluid, the velocity is constant across the channel. This plot shows the variation of pressure along the top and bottom channel walls computed on the fine grid. As the velocity along the top wall increases, the pressure reduces and vice versa. Due to the presence of an obstacle on the bottom wall, pressure first increases at the front stagnation point before decreasing rapidly toward the obstacle top. The variation on the downstream side should be fully symmetric, which is, for the finest grid, almost true. The pressure is much lower at the top of the obstacle than at the opposite wall, because the velocity is the highest at the obstacle top. Sufficiently far away from the obstacle, pressure is equal at both walls, and the same upstream and downstream of obstacle. There is no pressure loss. Because the pressure is symmetric around the obstacle, the net force on obstacle in x direction is equal to 0, which is of course not realistic. These plots show the variation of the tangential velocity along the top and bottom channel walls computed on the three grids, coarse, medium and fine. On the coarse grid, there is a significant difference in velocity at the two walls downstream of the obstacle. They should be equal in an invested flow. As the grid is refined, the error becomes smaller and the velocities are almost equal at the fine grid. In these computations, the second-order discretization was used for all terms in the Euler equations. These two plots show the variation of the tangential velocity along the top and bottom channel walls computed on the fine grid using the first-order discretization method for convection terms, which is the first-order upwind scheme, and the second-order discretization, which is the linear upwind scheme. The first-order upwind scheme introduces numerical diffusion, which leads to a very large error in the solution downstream of the obstacle. Even on the fine grid, the velocities on top and bottom wall differ by about 18%, while the difference is smaller than 1% when the second-order scheme is used. The first-order discretization method should be avoided when solving the Euler or Навье-Stoksa equations. These two plots show the velocity contours computed on the fine grid using the first-order discretization for convection terms and second-order discretization. The solutions are almost the same on the upstream side of the obstacle. The differences become apparent above the obstacle top and are especially large on the downstream side. The solution obtained with the second-order scheme is perfectly symmetric around the obstacle at the top wall as required for an invested flow, while the solution obtained with the first-order method is obviously over-diffusive on the downstream side. Near bottom wall, the contours from the second-order scheme exhibit oscillations, while in the solution obtained with the first-order method the error spread all the way to the outlet. The conclusions from this lesson can be summarized as follows. Invested flows can be computed using Simcenter STAR-CCM+ by setting fluid viscosity to 0 or by using the invested flow model. Euler equations are then solved instead of the Навье-Stoksa equations. Invested flows are not fully realistic, and simulations of such flows are seldom used in practice, except when specially tuned to a particular application, like for example in some design tools for propellers. For some invested flows there are analytical solutions. They can be used to assess the discretization errors in numerical solution methods. Even where analytical solutions are not available, like in the present case, the knowledge about the properties of invested flows is useful for the analysis of discretization methods. Thank you for your attention. Lesson 4. Simulation of laminar flow. This lesson is about simulation of laminar flows in ducts with a variable cross-section geometry. The main objectives of this lesson are to apply a CFD tool, here Simcenter STAR-CCM+, to simulate the laminar flow at a Reynolds number equal 133.3 in the selected test case. To analyze the obtained solutions to understand the flow physics. To evaluate the accuracy of solutions by comparing results obtained with different grids. To explain the influence of the order of discretization scheme on the accuracy of solution, and to recall the difference in flow features compared to the invested flow from lesson 3. The following physics models were selected for this simulation. Steady-state flow, constant density fluid with a density of 1 kg per cubic meter, laminar flow, segregated flow solver, which means sequential solution of equations for velocity components and pressure correction, or coupled solver, which means coupled solution of all equations. Both first-order and second-order upwind schemes for convection fluxes were tested. The following conditions were imposed at boundaries of the solution domain. Symmetry for front and back planes to impose two-dimensional solution. The solution domain is a 2 mm thin slice with one layer of cells. No slip wall for top and bottom channel wall and the semi-cylindrical obstacle. Velocity inlet at the left boundary. The parabolic velocity profile of a fully developed laminar flow in a plane channel was specified, which is an analytical solution of the Навье-Стокса equations for fully developed flow conditions. And outlet condition at the right boundary, which means zero gradient in flow direction, will impose the same flow rate at outlet as at inlet. The maximum velocity in the parabolic inlet velocity profile was 2 meters per second, which means mean velocity of 1.33 meters per second, which leads to the Reynolds number of 133.33. These two plots show the distribution of computed pressure and the streamwise velocity component. Note that pressure distribution is not symmetric, hence there is a non-zero net force on the obstacle in flow direction. In an viscid flow, the pressure distribution is symmetric and the net force is zero. The velocity distribution is also highly asymmetric, with a reverse flow direction in part of the wake. For the same mean velocity, the maximum velocity in a laminar flow is higher than in an inviscid flow. Even in a straight channel without any obstacle, the maximum velocity in a laminar flow is higher than in an inviscid flow, where the velocity is constant across the channel. In the parabolic profile of a laminar flow, the maximum velocity at the symmetry plane is 1.5 times higher than the mean velocity. Note also the existence of boundary layers at walls and shear layer between the core flow and the recirculation zone. These plots show the visualization of the flow by streamlines and line integral convolution. Note that there is a very strong recirculation behind the obstacle and a weak one in front of it. Flow separation points are denoted here by S and reattachment points by R. This plot shows the variation of the shear stress along the top and bottom walls computed on the fine grid. The shear stress at the top wall, here denoted by the red line, increases as the flow approaches the narrowest cross-section above the obstacle, where it is about 5 times higher than in the straight channel. Thereafter it reduces below the level of the undisturbed channel flow, and then recovers again to attain at the end the same value as in front of the obstacle. The shear stress at the bottom wall, here denoted by the blue line, decreases gradually as the flow approaches the obstacle. It becomes zero at the first separation point, is zero then again at the front stagnation point, and increases then rapidly along the obstacle to reach its maximum shortly before the top of the obstacle, where it is about 10 times higher than in the straight channel. The shear stress reduces then rapidly as the flow goes around the top of the obstacle, becomes zero where the flow separates from the obstacle, is zero then again shortly before the rear stagnation point because there is a tiny recirculation here in the corner. It increases again within the recirculation zone, becomes zero at the reattachment point, and then increases gradually to reach the value of the fully developed channel flow. Assigned tangential shear stress vector component is changing sign at separation and reattachment locations. If it was plotted instead of the shear stress magnitude, the blue line would look like this. It would cross the zero line here, where the separation takes place at the obstacle wall, come back and cross the zero line where the reattachment of the tiny recirculation of the obstacle is, cross the zero again where the separation at the bottom wall begins, stay on this side within the recirculation zone, and then cross the zero line again at the reattachment point. This plot shows the variation of pressure along the top and bottom channel walls, computed on the fine grid. As the velocity near top wall increases, the pressure reduces, and vice versa. Due to the presence of the obstacle on the bottom wall, the pressure first increases at the front stagnation point, before decreasing rapidly towards the top of the obstacle. On the downstream side of the obstacle, the pressure recovers, but not as much as in an inviscid flow. A local pressure loss occurs due to the geometry change and fluid viscosity. The steady pressure drop in a straight channel is also visible from the slope of the pressure profile. The additional pressure loss due to the obstacle is visible as the distance between lines corresponding to the linear pressure drop of the fully developed flow upstream and downstream of the obstacle, Without an obstacle, the straight line from the upstream side would simply extend all the way to the outlet. Note that a fully developed flow has not yet been reached at the outlet. A longer channel would be needed for that purpose. These two plots show the comparison of pressure variation along the bottom wall and of streamwise velocity component profile along the line at x equals 0.14 meters, computed on three systematically refined grids using second-order upwind discretization. The three lines are hardly distinguishable from each other, indicating that the grids are fine enough and that the solutions on medium and fine grid are very accurate. These plots show the comparison of pressure variation along the bottom wall and of streamwise velocity component profile along the line at x equals 0.14 meters, computed on three systematically refined grids using the first-order upwind discretization scheme for convection fluxes. Downstream of the obstacle, differences between solutions from different grids are significant. The difference between fine and medium grid solution is half the difference between medium and coarse grid solution, as expected of a first-order discretization method. Here the errors on the fine grid are not very large, but it is problem-dependent. In flows dominated by recirculation, the errors may be much larger, as will be shown in another lesson. The first-order method should not be used in practical applications, because the second-order scheme provides a much more accurate solution at the same computing cost. The conclusions from this lesson can be summarized as follows. Laminar flows are found in many applications, whenever is the Reynolds number smaller than the critical value for the particular geometry and flow conditions. An accurate prediction of laminar flow can be obtained by solving the Навье-Stoksa equations on a moderately fine grid using second-order discretization methods. A laminar flow differs significantly from an inviscid flow. It exhibits flow separation, recirculation, boundary and shear layers, and a pressure loss in flow direction. First-order discretization methods for convection fluxes should be avoided because they require much finer grids to reach the same level of accuracy than the second-order methods. Thank you for your attention. Lesson 5. Simulation of turbulent flow. This lesson is about the simulation of turbulent flows in ducts with a variable cross-section geometry. The main objectives of this lesson are: apply a CFD tool, here Simcenter STAR-CCM+, to simulate the turbulent flow at the Reynolds number of 1 million in the selected test case. To analyze the obtained solutions to understand the flow physics, like flow separation and recirculation in front and behind the obstacle, losses due to fluid viscosity and turbulence, etc. To evaluate the accuracy of solutions by comparing results obtained with different grids. To explain the influence of the order of discretization scheme on the accuracy of the solution for the given computational grid, and to recall the difference in flow features compared to laminar flow from lesson 4. The following physics models were selected for this simulation. A constant density fluid, water with density of 1000 kg per cubic meter and dynamic viscosity of 0.001 Pascal second. Turbulent flow with k omega turbulence model and wall functions. Segregated flow solver or coupled solver, steady state flow. Both first order and second order discretization schemes for convection fluxes are tested. The following conditions were imposed at boundaries of the solution domain. Symmetry for front and back planes to impose two-dimensional solution. No slip wall for the top and bottom channel walls and for the semi-cylindrical obstacle. Velocity inlet at the left boundary, where constant velocity is specified. Pressure outlet at the right boundary, where constant zero pressure relative to the reference level is specified. These plots show the distribution of pressure and the streamwise velocity component computed on the fine grid using the k omega turbulence model. Note that the pressure minimum and the velocity maximum are upstream of the highest point on the obstacle, and that isobars are not orthogonal at the obstacle wall. These plots show the visualization of flow using streamlines and line integral convolution, computed on the fine grid using the k omega turbulence model. Note the strong recirculation behind the obstacle, enclosing another weak recirculation at the re-stagnation point. A recirculation zone is also present in front of the obstacle due to the adverse pressure gradient there. It encloses another micro recirculation at the front stagnation point. The front recirculation zone would not be present if the bottom wall was replaced by a symmetry plane. For the creation of a recirculation zone, both adverse pressure gradient and a wall in flow direction need to be present. The separation and reattachment points are here marked by S and R respectively. This plot shows the distribution of turbulent kinetic energy and turbulent viscosity ratio, computed on the fine grid using the k-omega turbulence model. Note that turbulent kinetic energy is low where velocity gradients are low and has a maximum value above the center of the recirculation zone. The maximum turbulent viscosity is 13,537 times higher than fluid viscosity. This plot shows the variation of shear stress magnitude along the top and bottom walls computed on the fine grid using the k-omega turbulence model. Near inlet boundary, wall shear stress is higher than in a fully developed flow because a constant velocity was specified at the inlet, resulting in very high velocity gradients in the direction normal to walls. The shear stress at the top wall increases as the flow approaches the narrowest section above the obstacle, where it is about 5 times higher than in the straight channel. Thereafter, it reduces steadily towards the solution for the fully developed channel flow. At the bottom wall, the shear stress reduces as the flow approaches the obstacle. It is zero at the separation point of the front recirculation zone, is very small within the recirculation zone, and is zero again at the front stagnation point. It then increases rapidly as the flow accelerates over the front of the obstacle and reaches the maximum value shortly before the top of the obstacle, where it is about 10 times higher than in a straight channel. It then reduces rapidly on the rear side of the obstacle to zero at the separation point, is small within the tiny recirculation zone near the rear stagnation point, increases within the recirculation zone, becomes zero again at the reattachment point, and then increases gradually toward the fully developed state. When a fully developed state is reached, the shear stresses at the top and bottom wall will become equal. The channel in this simulation was not long enough to reach the fully developed state. This plot shows the variation of pressure along the top and bottom channel walls computed on the fine grid using the k-omega turbulence model. As the velocity near top wall increases, the pressure reduces and vice versa. Due to the presence of an obstacle on the bottom wall, pressure first increases at the front stagnation point before decreasing rapidly towards the obstacle top. The minimum pressure is found shortly before the top of the obstacle. On the downstream side of the obstacle, the pressure recovers, but not as much as in laminar flow. The local pressure loss due to the obstacle is much larger than the loss due to friction in a straight channel. In the case of laminar flow, they were comparable. See lesson 4. This plot shows the comparison of pressure variation along the bottom wall and of shear stress along the bottom wall computed on 3 systematically refined grids using the k-omega turbulence model and second order affine discretization for convection fluxes for all variables. Differences between solutions on different grids are much larger than in the case of laminar flow. High shear stress at the inlet is due to the specified constant velocity there. As the grid is refined, the gradient at the first near wall cell appears larger because the velocity is zero at the wall, which is why the shear stress increases here as the grid is refined. The pressure is set to zero at the outlet. This is why pressure at the inlet increases when the grid is refined. These plots show the comparison of profiles of the streamwise velocity component and turbulent kinetic energy along a vertical line at x equals 0.14 meters, computed on 3 systematically refined grids using the k-omega turbulence model and second order affine discretization for convection fluxes for all variables. Differences between solutions obtained on different grids are much larger than in the case of laminar flow. Although the grid 3 is relatively fine, the solution would still change appreciably with another grid refinement. The difference between profiles obtained on grid 2 and 3, medium and fine, is much smaller than the difference between profiles obtained on grids 1 and 2, coarse and medium, indicating the convergence toward a grid-independent solution. These plots show the comparison of solutions on the medium grid using different combinations of discretization schemes for convection fluxes for the profile of u velocity at x equal 0.14 meters and for the shear stress on the bottom wall. Black line indicates solutions when the first order scheme is used for all equations. Red line indicates that the second order scheme is used in all equations, and blue line indicates that the first order scheme is used for k and omega and the second order scheme for momentum equations. Discretization of convection fluxes in momentum equations has the greatest effect on the solution accuracy. The difference between solutions obtained using the first and the second order method is very large. Because the source terms in equations for k and omega are functions of velocity gradients, it is important that the velocity field is accurately predicted. The difference between solutions obtained when convection is discretized with second order in all equations and when convection is discretized with first order in equations for k and omega only is very small. The blue and the red line are very close to each other. The conclusions from this lesson can be summarized as follows. The turbulent viscosity varies 4 orders of magnitude within the solution domain. Turbulent kinetic energy is generated in boundary layers near walls and to a much higher degree in shear layers and obstacle wake. The grid dependence of solution is much stronger when the flow is turbulent than when it is laminar. The order of discretization for convection terms is most important for momentum equations and less important for turbulence model equations because the latter are dominated by source terms which depend strongly on velocity gradients. Thank you for your attention. Lesson 6. Computational Efficiency, Laminar Flow. This lesson is about computational efficiency related to simulation of laminar flows. The main objectives of this lesson are to explain how the choice of under-relaxation factors in the segregated solver and CFL number in the coupled solver affects the computing effort for a given computational grid. To distinguish how the grid fineness affects the computing effort for a given set of other parameters. And to interpret how the initialization of variables on a given grid affects the computing effort required to reach the desired level of residuals. This plot shows the influence of the under-relaxation factor for pressure on convergence of iterations when computing the flow on the medium grid using the segregated flow solver and the under-relaxation factor for velocity set to 0.8. For a given under-relaxation factor for velocities, here 0.8, the number of iterations required to reduce the residual norm for u velocity below 10 to minus 5 reduces slightly as the under-relaxation factor for pressure is increased from 0.1 to 0.5. However, if the under-relaxation factor for pressure is further increased to 0.6, then iterations diverge. This is the typical behavior, but the range of usable values depends on the flow and grid fineness. It is narrower for finer grids. This plot shows the influence of the under-relaxation factor for velocities on convergence of iterations when computing the flow on the medium grid using the segregated flow solver and suitable under-relaxation factor for pressure. Shown is the history of residuals for u velocity. Other residuals reduce at the same pace. However, with under-relaxation factor for velocities above 0.95, the mass residual reduces slower than the residual for u velocity. For a given grid, convergence is faster when the under-relaxation factor for velocities is increased up to a certain limit, beyond which convergence becomes again slower or iterations diverge. The optimum depends on the flow being computed, the grid fineness, it is lower for finer grids, and the grid quality, it is lower for poor grid quality. In this case, the convergence was fastest when the under-relaxation factor for velocity was increased to 0.98. Further increase to 0.95 or 0.995 required again more iterations. The under-relaxation factor for pressure needs to be reduced as the under-relaxation factor for velocities is increased. The nearly optimal relation is under-relaxation factor for pressure equal 1 minus under-relaxation factor for velocities. This plot shows the influence of grid fineness on convergence of iterations when computing the flow on systematically refined grids using the segregated flow solver and the under-relaxation factor for velocities set to 0.9 and for pressure to 0.2. The required number of iterations increases over proportionally when the grid is refined. The same ratio would be obtained if another under-relaxation factor for velocities was used, as long as it is kept the same on all grids. This plot shows the influence of the CFL number on the convergence of iterations when computing the flow on a medium grid using the coupled flow solver. The default value in Simcenter STAR-CCM Plus is conservative. It is worth looking for optimum if many simulations are to be performed. For a given grid, the convergence of coupled solver is faster when the CFL number is increased up to a certain limit, beyond which the convergence becomes again slower or iterations diverge. The optimum value of CFL number depends on the flow being computed, the grid fineness, it is lower for finer grids, and the grid quality, it is lower for poor grid quality. In this case, using CFL equal 10 would require too many iterations to reach the convergence criterion. CFL 100 is already better, but with CFL equal 1000, 3 times less iterations are required to reach the convergence criterion. Increasing CFL to 10,000 leads to another reduction of the required number of iterations. Note that the segregated solver with optimal under-relaxation factor for velocities equal to 0.98 also required around 200 iterations to reach the convergence. This plot shows the influence of grid fineness on the convergence of iterations when computing the flow on systematically refined grids using the coupled flow solver and CFL equal 1000. The required number of iterations increases over proportionally as the grid is refined. Similar ratios are obtained if another CFL value is used, as long as it is kept the same on all grids. The ratio is approximately the same for the coupled and for the segregated solver. These plots show the convergence of iterations when computing the flow on all 3 grids using the segregated flow solver and the under-relaxation factor for velocities and pressure set to 0.9 and 0.2 respectively. In one case, the initial solution for each finer grid was obtained by interpolation from the solution on next coarser grid. In the other case, the same initial solution was used for each grid, which was the parabolic velocity profile and constant pressure. By initializing the variables on each finer grid with the interpolated solution from the next coarser grid, initial residuals on finer grids are smaller and the total number of iterations required to reach the given level of residuals reduces significantly. For the fine grid, 500 iterations are needed with such initialization and 2400 iterations when using the same initialization as for the coarsest grid. The conclusions from this lesson can be summarized as follows. The segregated solver requires the setting of under-relaxation parameters for velocities and pressure, while the coupled solver requires the setting of the CFL number. Optimum values of these parameters depend on the problem being solved, grid fineness, and grid quality. Default values of these parameters in most CFD codes are conservative. They work for most flows, but are not optimal for any flow. It is therefore worth trying to use higher values, because that may significantly reduce the computing cost. Thank you for your attention. Lesson 7. Computational Efficiency, Turbulent Flow. This lesson is about computational efficiency related to the simulation of internal turbulent flows. The main objectives of this lesson are to explain how the choice of under-relaxation factors in the segregated flow solver affects the computing effort for a given computational grid, to distinguish how the grid fineness affects the computing effort for a given set of other parameters, and to interpret how the initialization of variables on a given grid affects the computing effort required to reach the desired level of residuals. These plots show convergence of iterations on the medium grid for laminar flow at Reynolds number equal 133.3 and for turbulent flow at Reynolds number equal 10 to 6 using the segregated flow solver and the k-omega turbulence model. Under-relaxation factors were in both cases 0.9 for velocities and 0.1 for pressure. In the case of turbulent flow, 0.9 for turbulence variables as well. Convection fluxes we discretize using the second-order upwind scheme. In the case of a laminar flow, residuals can be reduced down to the round-off level. After an initial period, the rate of residual reduction becomes constant as in linear problems. In the case of a turbulent flow, residuals cannot be reduced below a certain level. The residuals for continuity and momentum equations stall at 10 to minus 5 and for k and epsilon between 10 to minus 3 and 10 to minus 4. These plots show convergence of iterations on the medium grid for the turbulent flow at Reynolds number 1 million when using the segregated flow solver and the K omega turbulence model or K epsilon turbulence model, with convection fluxes discretized using first order upwind scheme for all variables. Under relaxation factors were 0.1 for pressure and 0.9 for all other variables. In the case of K epsilon turbulence model, residuals can be reduced down to the round-off level, but in the case of K omega model, they can't. The residuals stop reducing at some level. This can happen when using a high-order discretization with some turbulence models or on poor quality grids. Another cause is the inherent unsteadiness of the flow, like the tendency to create vortex shedding, the instability of the flow separation on a smooth surface, etc. Switching to a transient simulation mode helps in those situations. These plots show the profiles of the streamwise velocity component, turbulent kinetic energy, and specific dissipation rate at three cross-sections behind obstacle, at x equals 0.14 meters, x equals 0.3 meters, and x equals 0.45 meters. Note the extremely high gradients of all variables near walls and at the shear layer. High-order methods create over or undershoots when the profile exhibits sudden changes, for example at the marked location, and these often lead to convergence problems. These plots show the profile of u velocity at x equals 0.14 meters at different residual levels, and the residual history for the computational medium grid at the Reynolds number equal 10 to 6 using segregated flow solver K omega turbulence model under relaxation factors 0.1 for pressure and 0.9 for all other variables. Convection flux is discretized using second-order discretization scheme for all variables. Differences in velocity profiles plotted at the three iteration levels are too small to be seen in the plot. In most engineering applications, reduction of normalized residual levels to 0.001 is sufficient. Tighter convergence is needed for finer grids to ensure that iteration errors are sufficiently smaller than discretization errors. This plot shows the influence of the under-relaxation factor for velocities on the convergence of iterations when computing the flow on a medium grid using the segregated flow solver K epsilon turbulence model and suitable under-relaxation factors for pressure. Under-relaxation factors for K and epsilon are the same as for velocities. For a given grid, convergence is faster when the under-relaxation factor for velocities is increased, here from 0.7 to 0.8 to 0.9. However, this only works up to a certain limit, beyond which convergence becomes again slower or iterations diverge. The optimum value of the under-relaxation parameters depends on the flow being computed, the grid fineness, it's usually lower for finer grids, and on the grid quality, it is lower for poor grid quality. The under-relaxation factor for pressure needs to be reduced when the under-relaxation factor for velocities is increased. A nearly optimal relation is under-relaxation factor for pressure equal 1 minus under-relaxation factor for velocities. Increasing the under-relaxation factor for velocities from 0.8 to 0.9 halves the number of required iterations to reach the convergence criterion. This plot shows the influence of grid fineness on the convergence of iterations when computing the flow on systematically refined grids using the segregated flow solver K epsilon turbulence model and under relaxation factors 0.1 for pressure and 0.9 for all other variables. The required number of iterations increases over proportionally as the grid is refined. Here the solution on each grid starts with a guessed initialization of variables. A significant reduction of the number of iterations on finer grids can be achieved by starting the iterations on finer grids from interpolated solution obtained on coarser grids. These plots show the convergence of iterations in the segregated flow solver when computing the flow on all three grids using the K omega turbulence model and when computing the flow only on the fine grid. By starting on fine grid, With the extrapolated solution from medium grid, about 1,300 iterations are needed to reach the convergence criterion. When starting on fine grid with an initial guess, about 3,100 iterations are needed. Solving on a sequence of systematically refined grids is therefore more efficient, and it also allows the estimation of discretization errors by comparing the solutions obtained on each grid. The conclusions from this lesson can be summarized as follows. The segregated flow solver requires the setting of under-relaxation parameters for velocities and pressure. Optimum values of these parameters depend on the problem being solved, grid fineness, and grid quality. Default values of these parameters are in most CFD codes conservative. They work for most flows but are not optimal for any flow. It is worth trying to use higher values of under-relaxation for velocities, which requires reduction of under-relaxation for pressure. Iterations do not converge as smoothly for turbulent flows as they do in the case of laminar flows due to severe nonlinearity and coupling of all equations. Often residuals cannot be reduced below a certain level, especially when high-order discretization schemes are used for all variables. Refining the grid or improving its quality usually helps, or switching to a transient simulation mode if the inherent unsteadiness of the flow is cause of the trouble. Thank you for your attention. Lesson 8. Comparison of different flow regimes. This lesson is about the comparison of different flow regimes and the resulting consequences for the simulation of such flows. The main objectives of this lesson are to describe the difference between viscid, laminar, and turbulent flow in the same geometry, a channel with a semicircular obstacle on the bottom wall. To explain the need to know in advance which flow regime is present before attempting to perform a flow simulation, and to interpret the impact of the flow regime on the choice of physics models, grid design, and other simulation parameters. These plots show the distribution of pressure computed on the fine grid for different flow regimes in viscid, laminar at Reynolds number 133.3 and turbulent at Reynolds number 1 million. For the turbulent flow, the k-omega turbulence model was used. The pressure field is symmetrical around the obstacle if the flow is in viscid. On the upstream side of obstacle, pressure distribution is similar for turbulent and in viscid flow. In the case of laminar flow, pressure contours are almost orthogonal to the obstacle wall, but for turbulent and in viscid flow this is not the case. The gradient of pressure in the direction normal to wall can be quite large at some locations. These plots show the distribution of the streamwise velocity component computed on the fine grid for different flow regimes in viscid, laminar at Reynolds number 133.33 and turbulent at Reynolds number of 1 million, where the k-omega turbulence model was used. The velocity field is symmetrical around the obstacle if the flow is in viscid, except for some oscillations on the downstream side which are due to discretization errors. On the upstream side of obstacle, velocity distribution is similar for in viscid flow and for turbulent flow, except for the boundary layers near walls. In the case of laminar flow, the maximum velocity is about 2.62 times larger than the mean velocity. For in viscid flow, it is about 2.59 times larger, and for the turbulent flow, it is about 2.4 times larger. These plots show the visualization of flow using streamlines computed on the fine grid for different flow regimes. In viscid flow, laminar flow at Reynolds number 133.33, and turbulent flow at Reynolds number 1 million, computed using the k-omega turbulence model. The streamlines are symmetrical around the obstacle when the flow is in viscid. For viscous fluids, the flow separates from the obstacle and a large recirculation zone is formed in the wake. The recirculation zone is longer and the flow in it is more intense in the case of a turbulent flow. These plots show the comparison of pressure variation along channel walls computed on the fine grid for different flow regimes. In viscid, laminar at the Reynolds number 133.33 and turbulent at the Reynolds number 1 million computed with the k-omega turbulence model. There is no pressure loss in the case of viscid flow. Pressure is the same downstream and upstream of the obstacle. In the case of laminar flow, pressure loss due to obstacle is roughly the same as the friction loss. In the case of turbulent flow, however, pressure loss due to obstacle is about 5 times larger than the friction loss. These plots show the comparison of velocity profiles at x equal -1 diameter, x equals 0, which is above the obstacle, and x equal d, 1 diameter downstream of obstacle, computed on the fine grid for different flow regimes. In viscid flow, laminar flow at the Reynolds number 133.33 and turbulent flow at the Reynolds number 1 million computed with the k-omega turbulence model. The profiles are the same at x equal -d and x equal d if the fluid is in viscid, except for some numerical oscillations on the downstream side. This is expected because the flow is symmetrical around the obstacle. In the case of laminar flow, velocity profiles are very smooth everywhere. In the case of turbulent flow, boundary layers are much thinner than in the case of laminar flow. The flow is more uniform across the channel, and there is a strong peak in the profile above the obstacle. There is some similarity between viscid and turbulent flow profiles upstream of obstacle and above obstacle, except for the missing boundary layers in the viscid flow solution. However, on the downstream side, there is no similarity whatsoever between the three flow regimes. Also, the flow within the recirculation zone is highly different between the laminar and turbulent regime. The velocity profile within the recirculation zone is parabolic in the case of laminar flow, but when the flow is turbulent, the maximum velocity is found close to the bottom wall. The conclusions from this lesson can be summarized as follows. Viscid flow represents the limiting case of an infinite Reynolds number. The flow features on the upstream side of the obstacle are therefore to some extent similar between viscid and turbulent flow regimes. The exception are boundary layers near walls in a turbulent flow and a small recirculation zone near the upstream stagnation point. Viscid flow is symmetrical with respect to obstacle and no pressure loss occurs. Both viscous flow regimes result in flow separation of the obstacle wall, and a large recirculation zone is formed in the obstacle wake. The recirculation zone is longer and the flow in it more intense when the flow is turbulent. Velocity profiles are more uniform across the channel in the case of a turbulent than in the case of a laminar flow regime. Thank you for your attention.